Hello everyone, thanks for joining. I'm Yuvaraj Dhandapani, PhD student at IIT Madras. In today's presentation, I will try to talk about influence of mineral admixtures on hydration characteristics. So this is a brief outline of the presentation. I'll try to give some background, but Pranay has talked about it in great detail, so I will rush through it. Try to give a classification of SCMs, look at different factors which affect hydration characteristics, give a brief background about basic hydration mechanisms and what are the other possible interactions which can happen when you start using SCMs. What is the role of different SCMs on the early age hydration characteristics? And Pranay has rightly pointed out, you test for the SCMs and finally, when you end up using in concrete, you have to do further understanding or tailoring. So I'll talk about some essential characteristics which has brought in light in the last 5 years or so by means of proper gypsum correction for certain SCMs, post substitution of SCMs, and what is the influence of temperature on SCM reactions. So essentially the context is the projections from international communities have pointed out that consumption of cement is projected to grow nearly two-folds in terms of worldwide consumption, and about four-fold growth is expected in India alone. So we need to use a wide range of materials available basically for the four reasons: to meet the demand and possibly make effective utilization of all the resources, to elevate any kind of environmental impact associated with certain mineral admixtures or certain in the clinker production as such. And finally, we want to use more of this SCM in the concrete, mainly to draw advantage from its improvement which is brought about in the concrete performance. So we need a holistic understanding of all these four characteristics to make proper utilization of the resources in different contexts of application. Trying to give you a classification of different SCMs, I would put it as siliceous. So you can see a ternary chart of calcium, silica, and alumina. So these are the kind of SCMs which mainly have reactive silica alone in it. So you have silica fume which fits in right in there. You have vegetable ashes such as rice husk ash, bagasse ash, biomass ashes, even ground fine glass powder. Then you have other classes of SCMs where the reactive part of the SCMs contain aluminosilicate component in the amorphous content. So you have fly ashes which have reactive alumina and silica. You have calcined clay, bottom ashes, even volcanic ashes have certain amount of alumina in it. Then you have the other categories of SCMs which are calcium rich glasses. So you have calcium along with alumina and silica in the reactive component. So these will come right up here in the ternary chart. So because these have calciums, it's not going to as effectively consume calcium hydroxide as such. And as cement substitutes, more and more increasingly, we want to use all the possible options in terms of inert fillers as well. So there are fillers like limestone, base marble powders, quartz, even fine iron-rich slag, which are not so inert, can find a place in lower grade cement, like a 33 grade cement, as inert fillers in it. Essentially, in this raw material chart, the basic reactions that are meant to happen are between the alumina and silica and the SCMs along with calcium hydroxide, which kind of produce hydration products in this region. And then there are other reactions which are possible especially because of the alumina in the SCM with components such as calcite to produce hydration products in this zone. So we have a very confined zone where raw materials are available and hydration products are going to be formed. So what are the factors controlling the hydration process as such? So there are several intrinsic characteristics of the material itself, such as particle size distribution, which you can control to a great extent by means of grinding. The reactive content present in the SCM. So for example, slag is fully reactive material, whereas on the case of fly ashes, only a portion of fly ash is going to react. And the reactivity of the material, which is the rate at which the material is going to react over the period of time. There are other characteristics such as how you proportion this binder, like replacement level, whether you are going for a combination of cement substitute, what is the impact of water binder ratio on the hydration characteristics. And there is a whole range of other characteristics such as role of temperature, which governs SCM reaction, relative humidity, which is present inside the concrete or during the time of reaction, pH of the system, which will control the dissolution rate, the curing process to allow it to evolve, and certainly impurities such as magnesia or carbon in it, which can uh, have some impact on the hydration characteristics. Trying to give a context about what is the process of hydration, what essentially happens is it's a reaction process which leads to filling up of pore spaces. So if you take initially the cement particles, when we disperse in water, over the period of time, all this in between spaces, which are the capillary regions, get filled up with hydration product. Now we want to move towards blended cements, where a portion of the cement clinkers will be replaced by SCMs. Right? And what we know from literature is the reaction degree of the SCMs are much lower compared to your halite, which is a major cement component. So these are going to react much slowly, which means the reactivity of the material goes down. So you have to cure more to get the benefit, or simply put in perspective of space, the region to be filled by the pozzolanic reaction increases, and which happens much slower. Right? So trying to look at how the process happens over the period of time. So this is a typical chart which you will see in textbook, where initially you have formation of ettringite, CSH, and calcium hydroxide. And over the period of time, you start having a later reaction of pozzolans, which start having this most talked about pozzolanic reaction, which leads to consumption of portlandite and increase in pozzolanic CSH. But what we also need to understand is there is a whole lot of impact which SCMs can bring about during the main hydration period itself. For instance, addition of SCM can modify the reaction rates of the clinker phases. It can do some tweaking to the amount of ettringite which is precipitated in your cement systems. And there are other hydrate phases which can start forming, such as carboaluminates or stratlingite, which can have an impact on your performance. So this part of the interaction is most widely talked about. So in this presentation, what I'll try to do is give a major focus on what are the other impacts of the SCM onto the main hydration during the main hydration period in terms of other interactions. So generally, SCM hydration is assessed by a calorimetry experiment, where because cement being an exothermic reaction, you can measure the heat release rate, which give a good, fair enough estimates of the reaction rates. So you have the main hydration peak. This is the cumulative heat, which is the energy of the material. So you see a rapid increase in energy within the first 1 day, and then the reaction products slow down. So you have the main hydration region, where you have formation of early CSH, ettringite, and CH, and then the later hydration period, where you have later age CSH, pozzolanic CSH, and other hydrate phases. So when you try to break open at 1 day and put a piece of cement on microscope, this is how it looks. So these bright phases are unreacted cement. You can see that it started forming a lot of hydration products in between. And over the period of time, by 28 days, the microstructure of the cement as such becomes much more compact than what it is at 1 day. However, we need to understand that a major portion of the clinker reaction happens in the early ages. So let's look at what happens when we put an SCM or a mineral admixture into it. So these are some hydration curves with fly ashes at 30% and fly ashes at about 42%, and high volume fly ash. You can see because the clinker being less, the clinker reaction total heat flow is reduced, and there is also a delay in the increase in the heat evolution curve. So let's look at whether the addition of fly ash as such is having an impact on the reaction of the clinker phases. How do we do it? So we know the amount of cement which is present in the binder, and when we try to produce a normalized curve where the heat flow is normalized to the gram of cement present in the binder, this is how it looks. So we can see, irrespective of fly ash, the heat flow from per gram of cement is nearly similar, which confirms that a major portion of the cement is what is reacting. However, what we also notice is there is a slight shift in the peak to the right, which means the reactions happen slightly slow, at a slower pace. However, the major amount of fly ash remain inert during this period. So is all the SCMs react at the early ages? So we did an experiment on a range of different SCM. I have presented a typical result of a class F fly ash, class C fly ash, calcine clay, and slag. You can see fly ash curve over here. But when you start adding slag to it, because slag can start reacting right from the early ages, you can see the curve is not shifted to the left, which means the reactions start happening much faster. However, when you start looking at the profiles of calcine clay and the class C fly ash, you see the profiles more like a truncated core. So typically, to read this hydration curves, so what you see is a kind of a shoulder peak, a very small one here, but in the case of class C fly ash, you can see a dominant shoulder peak. This corresponds to the reaction of the aluminates. So basically, you have the main hydration curve from the C3S reaction, and then you have the aluminate reaction, which corresponds to the secondary formation of ettringite. So in these two cases, which will be the case in some SCMs, what happens is the aluminate reaction start happening before the main hydration period. So when this happens, the silicate reaction is affected. So basically, you have rapid dissolution of these SCMs, and it also has a higher amount of reactive aluminates. So it shifts the curve quite rapidly. So in these cases, what we have to do is, when we start increasing additional dosages of gypsum to it, so you can see the typical curve for the class C fly ash, and when you start increasing gypsum dosage, you can push this aluminate reaction. By doing so, we are also increasing, you can see the width of the silicate reaction is being increased, which means we are allowing the C3S reaction to happen properly. So when this happens, we do a small mortar bar strength test. You can see the strength test without gypsum, and when you start adding gypsum to it, because we are allowing the clinker reaction to happen properly, and ettringite amount which can get increased because of the addition of gypsum, 7-day strength can change from nearly 15 megapascal to around 25-30 megapascal. So by taking a closer look at the hydration characteristics, we can maximize the early age benefits from some of these SCMs. Of course, not all would have reactive aluminate, but the one which has reactive aluminate or reacts much faster should be looked at much closely, and the binder composition should be fine-tuned. The other aspect which I want to talk about is what is the impact of this hydration curve in terms of some characteristics. So you can see with increasing fly ash, the curve shifts to the right and the heat flow is less. So when you do a simple VCAT test, what happens is the penetration resistance starts shifting this side, which means an high volume fly ash binder has a delayed setting characteristics compared to a PC system. So when you start adding a minor dosage of limestone, Pranoy talked about limestone being a filler. So what happens is, despite being an inert material, it can accelerate the reaction of the clinker. So you can see the heat flow start becoming much closer to your clinker reaction. So when this happens, the setting time can be brought closer to your PC systems. So the performance can be tailored by proper co-substitution of SCMs. The early age hydration kinetics can be controlled, which controls the hardening characteristics, can be fine-tuned. And in general, the impact of limestone addition on the early age behavior is quite beneficial, which has been widely talked about in literature as well. So what is the impact when you start going towards co-substitution of SCM? So I give a hydration profile for the cement, for the fly ash system, which I talked about. So when you have just limestone in this system, you can see the acceleration in the clinker reaction. And when you start going for co-substitution, which is the brown dashed line you can see here, you can bring the cement clinker phases to react similar to your plain Portland cement. By doing so, overall, the early age hydration characteristics are modified for the better. And when you do a very simple assessment of compressive strength of concrete, you can see this is for the PC. When you go for a fly ash concrete, early strengths are much lower, and we obviously know that it will pick up in the due course of time. When you go for an additional replacement of clinker by means of limestone, 15% limestone, the strength difference, which is about 10 megapascal at 3 days, can be brought down to nearly 5 to 6 megapascal. So we need to have a judicious combination of SCMs, which can improve the concrete performance at the early ages. And we have also made assessment of the later age strength, which doesn't seems to be much different. So what it has to do with different binders. So here are some energy curves. So what you see is the energy curves of all blended cements are much lower at the early ages. And you can see the slag and calcined clay binders start picking up by nearly 2 days and reach a much higher energy than your fly ash systems, which means there is increased amount of reaction which is happening. And when you directly try to correspond it in terms of a major concrete property, you can see the strength difference at 7 days. So this is for the PC. This is for the fly ash cement, which is a typical PPC grade cement used. And you have a slag system, which has higher energy than fly ash, which will show a much higher strength development characteristics at early ages. And you have calcined clay limestone cement, which is the LC3 combination, for which a current composite cement standard is under progress, which will eventually come out in due time. So the early pozzolanic reaction with these two SCMs start impacting the property from a very early age. And by using combination of these SCMs, as we can see here, you can improve the properties of your concrete systems right from a very early period. So what are the other impacts? Like, for instance, in role of temperature. So this is a microstructure of a fly ash cement, which is reacted at typical laboratory conditions at 20 degrees Celsius. So the spherical particles which you see here are all unreacted fly ash particle, which will react in the due course of time. So when the same system is kept and allowed to react at 40 degrees Celsius, you can see a much more compact and dense structure, because the pozzolanicity of the SCM is accelerated. So we can naturally think of why a lot of rapid assessment test methods, like the one Pranay talked about, chose to have higher temperature to assess the SCM characteristics at a much faster pace. So for example, the highest standardized test of lime reactivity assess the strength development of mortar by 10 days at 50 degrees Celsius. Ian Frattini's test uses 40 degrees Celsius, and other rapid screening tests are done either at 40 and 50 degrees Celsius. So in order to maximize the benefit, so for example, use of SCMs will be beneficial when you start curing using these systems in steam cured condition, because the reaction of the SCMs will get accelerated in the because of the temperature. So let me come to closure. The major takeaways are, when you start using these SCMs in cement, there are other characteristics which you need to look at and make sure the reaction is proper. So hydration is affected by chemical composition and reactivity. Proper gypsum addition can maximize the benefit in blended cement to a great deal in blended mineral admixtures with reactive alumina in it. This has major implications on early age properties. Co-substitution of SCM is a very promising measure to take advantage of complementary interactions. And this obviously necessitates that IS standards should facilitate adoption of such composite binders in the due course of time. and the efficacy of the SCM reaction improves with temperature, and this could have a major impact on the microstructural development. And obviously, I want to make this point clear. There is no one fit all. By means of better hydration characteristics, we are not necessarily talking about durability. It's more a step towards understanding the reaction processes, develop or intervene to tailor the binder formulations. Durability performance is complex, as Prashant will talk about in the later presentations, and it's more specific to different exposure environment. With this, I'll bring you a note for those of you interested to read about mineral admixtures to this TC238 document, which is available in Rilem website. And thank you, everyone, and I'll be happy to take questions.
Thank you, Yuvaraj. So there are a lot of questions coming. I think, well, I'll take some of them. One was about the packing.
Yes.
Is there any model that can be used for the dense packing? So you talked about packing and the
yeah.
For that. Now, is there some model that people can use for this packing?
Yeah, so improving the packing efficiency does have an impact on early age properties. So there are some softwares available, open source. I don't want to bring name of any particular software in the presentation, but there are plenty of open source software available from different companies and research institutes, which can be used to pack different ingredients together to maximize the benefit.
Okay. And how about the fines? Does the grain size distribution of the SCMs affect their performance?
Yeah, so we did an assessment of range of different fly ashes. What we generally see is in calcium-rich mineral admixtures, when you make it finer, it does have an impact. But in general, class F fly ash, we don't see a major impact just by grinding the fly ash to a finer extent on the main hydration curve. But eventually, using a finer SCMs will improve the properties at much early age in terms of durability.
Okay. Then we normally consider limestone and quartz as inert material.
Yes.
Now, you have shown that limestone can be used. So can we say that quartz also could have some advantage?
Yeah, so we need to understand both quartz and limestone slightly from a different perspective. Quartz is just inert silica. So it's just going to have an effect of packing, not necessarily any impact on the hydration characteristics apart from packing and some acceleration. But when you come to limestone, major component is calcite particle, which makes limestone. And because of the calcium surfaces, it is going to allow nucleation of CSH happen on the cement surface, which is why you see a major shift in the hydration curve when you start using limestone compared to quartz or even class F fly ash, which is a reactive material.
Okay. Question from Dr. Rajamane. He asked whether the cement hydration itself is being modified by the SCMs.
Yes, that's what we talked about when I was discussing with more reactive SCMs, like in the case of silica fume, metacrylene, or the class C fly ash, which we saw. The SCM reaction happens harmoniously with the cement reaction. So they start reacting right from early ages, which means your pozzolanic reaction is going to happen right from the time the SCM start dissolving. So we need to classify that in the cement itself and start understanding different materials when it will start impacting the hydration of the blended cements.
Okay. What is the effect of temperature? Is it that the SCMs will work better at higher temperature or lower temperature? Is there some information about that?
Yeah. So basically, in terms of field perspective, you don't have a control on temperature. But as a parametric study, we need to understand when you do a lot of laboratory experiment as standard condition in, for example, typical summer in India, you can see the temperature is almost 40 degrees Celsius. So you need to understand what happens to this material when the behavior of the material can change at different temperature. And what we clearly see is when SCMs are put at higher temperature, it's going to react or dissolve much faster and make a much more prominent impact than what can happen at a lower temperature.
Okay. Uh, I'll ask, maybe combine a couple of questions in terms of LC3.
Yes.
Uh, how does it compare with regular cement, or what can you summarize as the major differences?
In terms of LC3, it makes use of two of the most impactful SCMs on the early age characteristics, like limestone, inert, but it has a major impact on the early hydration characteristics. Calcined clay, which also start reacting from a very early age. You can see the impact of calcined clay right from 3 days, for instance, like I showed in the energy curve. So by making use of both this material, which can make an impact at the early age, the LC3 can start producing strength development mostly on par with your plain Portland cement, which you don't necessarily see with a lot of other blended cements. Of course, in terms of durability, like chloride, all the blended cements are going to perform better, and there is no one better than other. But obviously, all blended cements are meant to be used in terms of exposure to chloride environments.
Okay, thank you, Yuvraj. So one clarification which just came in from Professor Suraneni that I'd like to summarize. So when he and probably Yuvraj talk about inert materials, they are calling as inert materials materials that do not show pozzolanic or hydraulic reactions by themselves. So
Yes.
thank you for clarifying, Pranoy. So I think when they are saying inert, they are not saying it's useless material, and
Yes.
it could still modify the cement hydration, as rightly pointed out by Pranoy and Yuvraj also. So they could affect other reactions, but by themselves they are not either pozzolanic or hydraulic.
Exactly.
Yeah, yeah. Thank you very much, Yuvraj. Now we'll go on to the next presentation by Professor Piyush Chaunsali.